Welcome our viewers. My name is Basalira Joshua. I'm a fellow from School of Statistics and Planning, and I'm doing quantitative economics. We are here for our presentation in time series, particularly the seasonality component. And I believe by the end of this video, you will have learned something. Yes. Before we go any further, allow me tell you the prerequisites for this presentation. One, you should have some basic mathematics and statistics, and we are going to use the language R. It's a statistical software. I believe majority of you know it. Of course, you should have a working computer and also a positive attitude, because there will be a lot to learn. Yes. And also, what we are going to cover in this presentation, first of all, we shall decompose a time series, and we shall discuss the different decompositions in a time series, that is the additive and the multiplicative, and we shall do some little bit of modeling of the seasonality component. Yes. And on top of that small introduction, as you all know, a time series, these are data points that are observed on the same variable over a long period of time. Now, this variable here, it could be a trend, it could be a cyclic, it could have a seasonality. And on Math in Motion, I believe you have, if you have been following, my colleague has discussed the trend component, and I'm here to discuss the seasonality component. Now, question is, what is the seasonality component? Yes, before we get to that, let me introduce to you the platform of R that we are going to use. R as a software, most importantly, it has 4 sections. The first one is on the top left corner, and that is where we write our R scripts, and below that is where we have the console, and the console is where we run our commands. And on the top right corner is where we have our environment, and it is that section that shows us which variables we have, which data sets are loaded. Yes. And below that we have a section for our plots, the packages, and the files. That is on the bottom right corner of my screen. This one here. This is the console here. This is the section where we write our script, and this is where we write the console where we write where we run our codes. This is the environment, and this is the section for our plots, files, and packages. This is important because you need to follow through. First of all, we have decided to use R in this section because R is very flexible, and also, if you notice in most books of time series, you realize that they've adopted R so much because R has a variety of packages, and its ability to visualize data very well. So with all those reasons, that's why we are using R. So let's get to it already. So in your course of time series, there are things at least you should know. That is the foundation, the models you should use, and also stationality. And also, after you attaining that model, you need to evaluate it and see how well it is working. And in this case, that's why we have called this the bigger picture, or the big picture, whereby you should be able to visualize your time series, the components in your time series, and also the decomposition of the time series. And in the middle section of seasonality and the model selecting, you should know the concept of stationarity. There is a concept called differencing. We shall also come later in the future and we discuss more about it. And when you know whether you have stationarity or non-stationarity in your time series, you should ask yourself, which model should I use that will suit stationarity. All that shall be covered here at Math in Motion. Stay put and enjoy. Now, first things first, before you do anything on a time series, you should know the properties of that time series. How does it look like? And that is why it is important to visualize your time series. And that is what we are calling our time plot. Yes. And if you look at your screen, there is an author called Rob. There are two actually, Rob and George, in their book of time series practices. They say that the first thing you should do in any data analysis task is to plot the data. Graphics enable many features of the data to be visualized, including patterns, unusual observations, changes over time, and relationships between variables. A time plot not only emphasizes patterns and features of the data, but can also expose outliers and erroneous values. And to put this in practice, we are going to use a dataset in R. That dataset, it is about the passengers received by an airport over time, from a period of around 1940 to around 1960 something. Yes, and that plot, you are seeing it here on the left of the screen. And as we have said that we are going to be using our R, let me show you how to visualize that data. Alright, so in our R script, this one here, we are having our dataset air passengers. We are having our dataset air passengers. Yes, I was saying I want to illustrate how we can plot our dataset, the air passengers dataset. Now, this dataset, first of all, just to get some kind of like introduction, as I've said, they are the number of passengers that an airport has been receiving over time. And why should this be of interest? This should be of interest because you realize that when you visualize this dataset, you will have a repeated pattern of passengers on the different months. So, to illustrate it, I've already written the code here in our script, and I've loaded it already. This is that is line 2 and 3. So in order to run these two lines, you will need to highlight them, and you press your Control Enter command, and you realize that on the corner here, our graph will be visualized. So that is on visualization, and that is how you can visualize. Yes, let us proceed. Now, that is the time plot, right? Now let us dive deeper into seasonality. Seasonality is the presence of patterns of fluctuations slash variations that occur at specific regular intervals. And these intervals can be weekly, monthly, quarterly, from year to year. Now, usually students confuse seasonality and cyclic, but seasonality happens within a year. It could be weeks, it could be months, it could be quarterly, but as long as it is within a year. I don't want to serve food when it's not yet ready, but the cyclic component will be presented next. And just to give you a hint, a cyclic component usually happens over a year, right? Yes, might be a lot of similarity in both, but that should be the first difference you notice. And this one, the seasonality, is within a year. Yes. Now, seasonality, of course, is affected by, in order to attain seasonality, there should be underlying factors that cause this seasonality. For example, we could have an example of success cards. You realize that a period around right now, or maybe next month of October, sales of success cards will increase, and could be the same to Christmas cards. Realize that there is that factor of maybe a public holiday or an event that happens again and again, that drives the sales of particularly maybe like the success cards or Christmas cards. And because of that repeated pattern, we realize in the sales, that repeated pattern is what we are calling the seasonality. And that could be seen in a number of things. We live with seasonality everywhere. Yes. The other thing is on how could we test for seasonality. Mathematically, seasonality, as I've said, first of all, seasonality could be seen from your visualization. When you visualize and realize that there is a consistent pattern you see every quarter of the year. Every quarter, same pattern happens. That illustrates what? Seasonality. But mathematically, you could use a parametric test, the Kruskal-Wallis test, and that could guide you and could help you test whether there is seasonality or not. Yes. Now, question is, what causes seasonality? Seasonality is caused by majorly two factors. Could be weather and temperatures. And the weather and temperatures usually affect a number of factors. Let us go back to sales. For example, people selling umbrellas. Now, you realize that in a year, there are months where we receive heavy rains, and there are months where we receive the dry season. And realize that there are those seasonal goods, such as the umbrellas, raincoats. They will receive more sales at a period such as that when they are receiving heavy rains. Why? It's because that's when people buy the most, and that's when the need is there. And because of that consistent, that the weather will not change all over just at once like that, it will continuously cause a seasonality. You see, you will continuously notice that same pattern of in the sales of those umbrellas, or let me call them seasonal goods. And we could see that also in agriculture. Agriculture produce is highly affected by weather and temperature changes. Yes. On periods of the wet season, people are able to produce, and yes, we receive a boom of agriculture output. It could be maize, it could be bananas. Yes, and in the dry spell, people don't produce, and of course, we don't receive as much. Yes, and now because of that consistent pattern, that is what we are calling seasonality. And you realize that the weather and temperatures are really very high. What? Very high causes of seasonality. Yes. The other reason could be calendar related events. These calendar related events could be public holidays, religious events, schools, day opening. Now, just to put it in context, in Uganda, usually when students are reporting back to school, you notice that the number of cars on roads at a particular point in time, or maybe during the day, usually those number of cars increase, and you will receive a lot of jam on such days when students are reporting back to school. And so if you are a researcher and you want to solve maybe a problem of traffic jam, and you maybe go collect data concerning number of cars on different days, probably you notice some kind of seasonality on the days when students are going back to school, and also when they are coming back from school. I'm talking of those in boarding, not those in day schools. Yes, those are the ones we are talking about. Also, we could talk about uh, calendar related events. It could be like also Christmas. Christmas, you could maybe notice on meat sold on such days, Eid, Christmas. Realize that usually these guys experience an increase in sales because there is a calendar related event like Christmas or Eid. And that calendar event is a major cause of such a seasonality. And yeah, partially those are the major two: calendar events and weather. Yes. Now, there is an important factor you should know about seasonality. There is something we are calling a seasonality factor. A seasonality factor or index is a number that measures how a specific season, it could be a month or quarter, compares to the overall average of a trend or trend level of the series. What I'm saying is, perhaps if you have an average of your trend or series, what will happen on your seasonality is, at the time when maybe the season, for example, maybe a particular quarter, and you receive maybe a high increase in maybe sales due to the seasonality, the seasonality factor is the one that tells us how far off is this increase from the actual trend. Now, that seasonality factor could be above or below. Yes. Now, for example, on this graph, you realize that in between these 2 years, 1950 and 1952, there is usually a decrease in the number of passengers. Just to increase it here. Yes. And now, if you have a particular trend, right? The seasonality factor is the one that will show us how far off is this data point from the actual trend. Same thing with these ones up here. How far off are they from this trend? That is basing on the seasons you have in your series. Just to illustrate what I'm talking about, let us try to illustrate that seasonality factor. Now, let me highlight this. Command enter. Yes. These figures down here are my seasonality factors. These are my seasonality factors. So you notice that too bad this one is not well labeled, but these are 12 months, and our year has 12 months. So this is probably January, February, March. So in a period around January, our factor is 0.91. What does that mean? That means that our factor here is 0.91, and the next one is 0.88. The next one is 1.007. Now, in order to interpret this, you get the difference between you get 1 minus the seasonality factor. In this case, if you get your your 1 minus your 1.007, you will get around, maybe let me correct this. If your seasonality factor is greater than 1, you get the 1.00736663 minus the 1. But if it is less than 1, you get 1, the figure, minus your seasonality factor. For example, 0.9. Let us begin with this one for January. It is 1 minus 0.99, 0.91, 023, 04. And we are getting 0.089. Now, the figure we get there, we multiply it by 100. And you realize that in this case, we are getting 8.97696, meaning that our values in around January, they are 8.976% below the figures we normally experience on our trend. And you could do that with all these figures. If it is greater, you subtract minus 1. The figure you get, you multiply it by 100. And that is by how much that figure will be off the trend. Yes. Just to give you a clear interpretation, it's here. If the seasonality factor for a season is above 1 by x, then we can conclude that the series value is 1 times 100% above the trend or average. If the seasonal factor for the season A is below by y, then we conclude that this x and y, this is the difference we have already got, right? And that's why they are multiplying that x by 100%. And that's the same thing with y here. That's the difference between your this one here and your what? And your seasonality factor. And you conclude that that series value is y by 100 below the trend value or average. Yes, I hope that's clear. Now, most importantly, we need to understand what this decomposition is. Remember, in my introduction, I told you that a time series could have a trend, it could have a seasonality, cyclic. Now, each one of these components of a time series could be modeled using either an additive model or a multiplicative model. So, if your time series has probably seasonality, right? There is a way you could remove that seasonality from a time series and remain with the trend and the error term. And such a model you can use is an additive model, whereby you add the trend plus the seasonality and the cyclic and the error term. And for a multiplicative model, you could multiply those components. Why is this important? This is important because yes, you might have seasonality, but you want to identify which other components does my series what have. So you find a way of removing the seasonality from the series and you remain with your trend. Now, this is how we illustrate the additive model, and this is how we illustrate the multiplicative model. We just multiply those different components. This is important when it comes to modeling, because in modeling you'll have to either select whether it's an additive model or a multiplicative model. Yes, you will have to specify it, whether you're using your starter or your R. You'll have to specify. Yes. The other question we need to answer is, when do you choose an additive and when do you choose a multiplicative? We select an additive. First of all, you need to first look at your what? Your graph, your time plot, right? For instance, let us look at this time plot we have here. One thing you will notice is that literally its trend is increasing at a certain proportion. There is some kind of like proportion that is being added on the previous values. So that proportion here that is increasing, this one here tells us that we should use a what? A multiplicative. But if this was increasing at a constant rate, this series was increasing at a constant rate, yes, time is passing, but the rate at which it is increasing has remained the same. There we'd use what? We use an additive model. But because here it is increasing by a certain proportion, we use a multiplicative what? A multiplicative model. Yes. Now, we have our series. How can we get the trend from our series? Now, yes, we shall discuss more about this in the future, but it doesn't kill for us to hint on it. You could use a moving average, whether it is a 4 moving average, 5 moving average, but as long as you're using a moving average, yeah, I think it can do pretty well to estimate your trend. And now, we are illustrating our trend with this small letter m with the underscript t. And when you estimate your trend and you want to remain with only the seasonality effect, you subtract the original values you had, which we are calling our x, minus this figure you have got from here, the trend. Please don't get confused. You have a time series and we are illustrating it as letter x, right? That is your time series the way it is. Whether it has seasonality, it has trend, that's the way it is. So you decide to do a moving average. When you do a moving average, you will get a column on its own, and that column is what is determining our trend. And actually, if you look here on the right, that small graph here is what probably from this graph here of the passengers. See how it looks like? But if you do a moving average, this is how it will turn to. You will remove off the seasonality component and you will remain with just a smooth trend. And that's how you will get these figures from using a moving average. Yes, and now as I've said, if you want to remain with only the seasonality effect, you get the original figure you had, which is the x, the original series with everything, the trend and the seasonality. Then you subtract off your moving average, this graph here. Then you will attain the figures you will remain with, that they will be the ones to illustrate your seasonal effect. And actually, if you illustrate them or visualize them, you will attain something like this, right? And actually, if you notice that this seasonality is increasing by a certain proportion, you see, the proportion by which it is increasing keeps on increasing year in, year out. And that is also another what? Another factor that should help you confirm that you should use a what? A multiplicative model when you notice such a thing. And whatever we are doing here is all decomposition of a time series, right? Just to put it to your notice, when you remain with this seasonality effect, that doesn't mean you are done. This seasonality will remain with some kind of error term. Some authors call it noise in your series, right? Yes. So this seasonality will remain with some noise or error term. Yes. And now if you want to get the error term on its own, you subtract the original series minus the trend minus the seasonality, and that will give you error term. And also for it, you can also visualize it. Realize that for it doesn't have a clear what? A clear pattern. It's literally like random, right? Yes. Yes. Now, just to illustrate everything that I was talking about, this code here, if we put it in our script, first of all, it will plot our series, the one for the air passengers, and it will also decompose this series into the trend, seasonality, and also the error term. But most importantly, we are not going to show the figures here how they will look like, but we shall visualize them. Probably that will give us a clear what? A clear image. So if you go back to your R, colleagues, I urge you to go back and try out these codes. Pause your video, write them, and run them. So this is the same code we have the other side. So of course, as I told you, highlight it and press your Control Enter. So we saw earlier that this same code gives us the seasonality factor here. And if you come to our plots here, right, the first thing you'll observe, they are calling it observed. Now this is our XT, our original series, the way it was. This is it, right? And if you do your moving, you compute your moving average, this is how it will look like. Of course, now these graphs come from figures, but just to give you might fail to notice from the figures, but the visualization will do. So that you realize that you are receiving a smooth trend. It is coming from a what? A moving average. And what you remain with is the seasonality and the error term, right? So realize that with R, just a few lines of code, you are able to decompose your series as illustrated by these graphs, right? So you will see them better when you run them on your computers, right? Try to make it a little bit bigger. So something like that, right? Yes. And also to notice here on this part of seasonality, you notice that there is some kind of repeating pattern, right? Between 1950 and 1952, that means the in between is around here 1951. Are you seeing this consistent rise here? Even here at the start of this 1951, it's increasing. 1952, it's also increasing. So you realize that consistent pattern there is what we are calling our what? Our seasonality. It is repeating itself year in, year out, year in, year out. And now when you notice here on the random, the error term, it doesn't have any kind of pattern. It's random, literally. So I hope that has illustrated our decomposition, right? Yes. Let's go back to our PowerPoint. Yes, this is the graph we have illustrated here, and this is the code you could use to run it. The other one was just a combination of all of them, and you realize that in this code here we stated that we are using a multiplicative what model, right, to plot that graph. Yes, now let's go to the most interesting part here in our presentation is what is modeling. Now in modeling, the seasonality, you could use the hot winters model, or you could use a model called SRMA. Yes. Now, to use the hot winter, which we are going to focus on, because for it doesn't have any prior knowledge you need to know, but the SRMA, of course, you need to have some kind of prior knowledge in the autoregressive, moving averages, which we are going to present here on Math in Motion very soon. But for now, let us look at this Holt Winter. This guy is Holt and Winter, very intelligent men. Holt did his model in 1957. Yes. Now, in order to go into modeling, let us first understand probably what exponential smoothing is. Now, this exponential smoothing, the way it works, it gives weights to values of our series. Now what it does, it gives more weights, heavier weights to more recent values, and less weights to the older values. As you go behind in time, the weights become smaller and smaller, and the weights become bigger as you come to the recent values. And partially that's how it works, right? And this exponential smoothing actually can help us also make forecast of our values. And if you notice here, this formula here, right, the weight alpha is being multiplied with the recent value at time t. Actually this one is this one is representing the value we are estimating, our value at time t plus 1, and so we multiply our alpha times y at time t, and the next weight is alpha in brackets alpha minus 1. We multiply it times the value of the value in our series at yt minus 1. So basically, the more we go in the past, the smaller these weights become. That is very important because it helps us define how this exponential smoothing works. So this exponential smoothing, as I've said, helps us to make our forecast, right? Yes. So this exponential smoothing is usually very good when you don't have a clear trend or a seasonal pattern. So for it doesn't mind. It will give you a forecast. And we could illustrate that in R here. Let us see. Let us create a new R script. Let us create our R script here. Yes, as saying, now we want to illustrate how we could forecast using our exponential smoothing. This is the script I wrote to help you make this forecast. We are going to forecast 5 values in the future, right? 5 values, that's 2014, 2015. And this data set is using the oil values in the period starting from 1996. And this forecast, as I've said, we are forecasting 5 values in the future, and this is the code we are going to use. The data set is concerning oil data, right? So you could try this, you could try and run it. Yes, as I've said, do that. So realize that it is quite very easy to use this R compared to maybe if you're using Excel. If you have your R, just write your R script, run it, and it will print for you your forecast. Right? So these are our figures. So just to make some kind of like small interpretation, right? It is giving us some kind of like confidence interval here, a 95%. These ones are the low figures, and these ones are on the lower bound, and this is the higher bound. So it is forecasting this same figure here, this figure here, and this is the bound it is giving us for them, these ones here. But now, one thing actually to note about exponential smoothing, when it forecasts a figure, it makes some kind of assumption that that figure will remain constant. If you forecast for 2014, that figure will remain the same for 2015, 2016. So it becomes literally what? It becomes literally like a constant. So when we come back to this graph, we're having this blue kind of like screen, and we have that blue line, that horizontal blue line, and that is our forecast. So literally it makes an assumption that when you count 2016, that figure will remain the same. 2017, it will remain the same. And because of that, that is that kind of like limitation for exponential smoothing. So for it could work for if you're forecasting maybe one figure or two. Yes. But now that is where this bound, this confidence interval comes in importance, right? Yeah. But if you're forecasting longer values, exponential smoothing won't do. But it can also help you forecast. Now, we have said this exponential smoothing doesn't mind whether you have trend or seasonality pattern. Now, what this guy Holt did, he advanced the what? The exponential smoothing, and he added in the component of trend. He used the exponential smoothing and added in the what? The trend. And he was able to make his forecast. But that is not where our major concern here. Our major concern is seasonality. And the person who was able to now model seasonality was Winter, who also improved on Holt Winter's method. How he did, he got the exponential smoothing, added on the trend got by Holt, and he was also able to model what? The seasonality. So basically, he added all the previous two to model his own, to make his own model, which they call the Holt Winters model. And now, let us see how we can make a prediction using the what? The Holt Winter. So most importantly here, Holt Winter models seasonality. And not just seasonality, for as long as there is some kind of like trend, on top of trend, he can model what? Seasonality. So that's why it is a powerful method for modeling seasonality. Now, let us see. Let us create here our R script, our new R script, and try and do model this what? And try and model it. Right? Too bad it is not running right away. Alright, now let's try and run our code here. Command enter. So it is giving us this illustration, right? Alright, so we come back to Holt Winter's forecast. We are going to use this code, this script I wrote, in order to be able to make this forecast. Yes. Now, this is the same code the other side. Don't get worried. As I said, we highlight it. We use our command enter. So for as long as your code is well written, everything is running, yeah, you'll get your figures. And now the only thing you have is to illustrate them. I mean, to interpret them. So you notice there is first of all a difference in how exponential smoothing did it and how hot winter does it. They are a bit different, though they are both forecasting. And on top of this code, we have received this graph. So this blue, these lines in blue here are the ones illustrating our values we are forecasting, right? These are our values we are forecasting, just to give you a clear picture through the visuals. And you notice that R is very powerful. It can help you do this in just a small click of code. And these are our values we have forecasted. This is from 1961, 1962, 63 and 64. Those are 4 years. 4 years for which we are forecasting. And it's saying for January 1961, the figures are here. Here. Yes. You take just a small break and try and run these codes and see. Yes, they might look obvious, but my friend, they need the time to practice and to learn. And these ones are our confidence interval. This is 80%, this is 95%. So you illustrate them. Yeah, basically that's it. Maybe just to show you what this code means, so it will take probably just a small interpret, something small. This first line of code loads our dataset air passengers. We create our object AP from the air passengers. Then the third one plots this graph we are seeing here. The third one plots our passengers dataset, the one we had previously. And now this one, the fourth line is the one that is modeling hot winters, and you have to specify that it's a multiplicative. And at the same time, if it was it needed the additive, you had to specify that it is additive. Realize the importance of the importance of the other decomposition we have studied. And so our forecast, we have put it in this object ap.h, right? We have created this ap.h, and it is the one going to model our forecast. So we also plot it. The fifth line, it is the one plotting this. And then now we bring in our forecast here. Our forecast, we put it in an object called ap.forecast, and if we print that object, we get our figures here, right? Yes. Yeah, actually that's it for now, but you should get time and try and do the codes. Yes. Yeah, actually that's it. I said lastly, we have the S-ARIMA model, though it will come in the future. Just stay tuned on the Math in Motion. A lot is coming. Please subscribe and share. Click that subscribe button. Yes. And as before we go, some of the references we have: Forecasting Principles and Practice. It's a very good book by Rob and George, 2018. We also have Introductory Time Series by Cowpart-Waite. So it's a very good book. Check them out. Thank you very much.
Yes, members.